Let us look at an example of sequencing n jobs on two machines. Raj Engineering Works has been given a contract to make 7 components by a client. Each of these components requires processing on two machines, M1 and M2, in the order M1, M2. So basically what this means is that Raj Engineering Works has been given a job or a contract by its client to make 7 components. Now each of the components is to be processed on two machines, M1 and M2, and the order in which it has to be processed is first it has to be processed on M1 and then it has to be processed on M2. Now the time in hours required by each of these jobs for processing on the two machines is given in a table, and what we have been asked is to find the optimal sequence for processing the 7 jobs. So basically the question is that given the times for processing on M1 and M2, which job should we process first and which job should we process second, and so on, so that the overall processing time is the minimum. So suppose this is your machine M1 and this is your machine M2, and there are 7 jobs to be processed: A, B, C, D, E, F, and G. Now each of these jobs has to be processed first on M1. So suppose you decide to process job D first. So D will be processed on M1 first, and it has been given that D will take 3 hours on machine M1. So it will take 3 hours here, and then after that it has to be processed on machine M2, and it has been given that D will take 5 hours on machine M2. So 5 hours here. So this is how we have to process each of these jobs, and the question is that out of A, B, C, D, E, F, and G, which one should be processed in what sequence? To solve this problem, let us use Johnson's rule. What this rule says is that first list the operation time for each job on both the machines. This in the problem we already have the time that each job takes on machine M1 and M2. Let us take a hypothetical example just to understand Johnson's rule. So suppose we have job A, B, C, and D, and these are to be processed again on machine M1 and M2 in the sequence M1, M2. And suppose the operation time are 2, 3, 5, 6, 7, 9, 10, and 1. So this is the operation time that is being mentioned in step number 1. Step number 2, select the shortest operation time. So in this case, suppose the shortest operation time is 1. And step 3 says, if the shortest time is for the first machine, do the job first. If it is for the second machine, do the job last. So it says, if the shortest time is for the first machine, do the job first, and if it is for the second machine, then do the job last. So what this is saying is, in this example, 1 is the shortest time. Now 1 is the shortest time, and that is relevant to machine M2. So this should be processed in the end. So let's assume that we are listing the sequence of jobs here. So at the end, we'll do job D. Now step number 4 says that repeat steps 2 and 3 for each remaining job until the schedule is complete. So repeat steps 2 and 3. So now we have already chosen D to be processed in the end. So let's cut this line. Now the 4th step says to repeat steps 2 and 3. So let's look at the other operation times to find the shortest time remaining. So the next shortest time is 2. Now 2 is to be processed on machine M1. So as per the rule, because this is to be processed on the first machine, let us process A in the beginning of the sequence. So A is to be processed in the beginning. Let's cut this line. From the remaining, the shortest time is 5. Again, this has to be processed on the first machine. So we'll put B after A. So this is B. We'll cut this. And the next remaining is C. So C will be done after B and before D. So the sequence in which we should process these jobs A, B, C and D is A, B, C and D. Now let us try to understand this rule in a different way. So let us first create a graph. Suppose this is our time in hours, and on the y-axis we have the machines. So below this line is M2 and above the line is M1. Now what this rule is saying is that if the shortest time is for the first machine, so there is a constraint given that the processing of each job has to be done first on machine M1 and then it has to be done on M2. So the first job that you do on machine M1, till that job finishes its processing on M1, you cannot process anything on M2. So here, as per this rule, if this time here is the shortest, then this time, that is the idle time on machine M2, will be lesser, and that is the key to obtain an overall lesser processing time. So the first part says that if the shortest time is for the first machine, do the job first. So here we are reducing the amount of time that machine M2 is idle for. Now suppose on machine M1 we process A, which is the shortest time. After A has been processed on M1, then you'll process it on M2. So suppose this is again A here. Now, based on the first part of this Johnson's rule, you would take the next shortest time on M1. So suppose you'll take B. So after A is finished on M1, you'll start processing B here. And after A is finished on M2, then you'll start processing B on M2. Now, if you look at M1, you are processing all the shortest times on M1. So what is happening here is that M2, the time is getting elongated because M2 is processing all the bigger times or the larger times as compared to M1. So in order to balance the times between M1 and M2, what Johnson's rule is saying is that if the shortest time is for the second machine, then do the job last. So suppose you take now another job, which is say D, which has the shortest time of 1 on machine M2. So if you process it here, so suppose this is C, or rather D, then the other time, that is 10, you will process on machine M1. So here this will take the maximum time, which is 10, and process D here. So eventually your M1 and M2 is balanced by reversing the shortest time on M2 starting from the last. Now in this example I have not used C. C would be somewhere around here and here, but I wanted to explain to you how starting from the end on machine M2 with the shortest amount of time on M2, basically you can balance the time taken by M1 and M2 such that the overall time taken by both the machines is the minimum. So for the given problem, let us first list the operation time for each job on both the machines. So we have jobs A, B, C, D, E, F and G, and time on machine M1 is 9, 5, 8, 3, 4, 1, 7, and time on machine M2 is 2, 4, 10, 5, 6, 11 and 6. So as per Johnson's rule, the next step is to select the shortest operation time. So in here the shortest operation time is this for job F. Now the next step on Johnson's rule says that if the shortest time is for the first machine, do the job first, and if it is for the second machine, do the job last. So here the shortest time is for machine M1, which is first in sequence. So we'll first process job F. So let's cut this line because we have already processed this. Now the next shortest number is 2. Now this 2 is on machine M2. So as per Johnson's rule, if the shortest time is for the second machine, do the job last. So we'll process A in the end. So let's put A somewhere here towards the end, and let's cut this line here. The next shortest time is 3, which is for job D. Since 3 is on the first machine, that is M1, we'll process D after F. So we'll put D here and cut the line. The next shortest is 4, which is for two jobs, that is B and E. Now B is on machine M2 while E is on machine M1. So there is no conflict. We'll put B before A because this is on machine M2, and E after D because this is on machine M1. And let's cut these two lines. From the remaining C and G, the shortest time is G, that is 6. Now this is on machine M2, so let us process this before B. So we'll put G here. Let's cut this line, and then only one is remaining, which is C. So we'll process this somewhere between E and G. So based on Johnson's rule, our sequence for processing these jobs is F, D, E, C, G, B, and then A. Now let us calculate the waiting time of the job. So waiting time of jobs. So let me put all the jobs in the sequence in which we decided to process them. So F, D, E, C, G, B, and A. These are the jobs. So to calculate the waiting time of jobs, we'll first plot the in and out time for both machine M1 and M2. So M1 in, out, and then M2 in, out. So let us first look at the in and out time for job F on machine M1. So for job F, machine M1 will take 1 hour. So if we start F on machine M1 at the 0th instance, then this will be finished by the first hour. So what this 0 means is that in terms of a watch, suppose we are starting at 000001. So this 00 is hours, then minutes, and then seconds. And what this 1 means is that when the clock hits 010000, where 01 is hours, then minutes and seconds. So when the clock hits 010000, then job F comes out of machine M1. Now when it comes out of machine M1, then immediately it can go into machine M2. So it will start at the first hour. This would be something like 010001, and as per the data given, the operation time on machine M2 for job F is 11 hours. So this will take 11 hours and it will be out on the 12th hour. Similarly for job D, on machine M1, we can start processing this at 1, and it's been given that D is processed on machine M1 for 3 hours, so this will be out at 4. Now while D is finished processing on machine M1 at 4, but M2 is still busy processing job F. So once job F is finished at the 12th hour, then it can process job D. So in time is 12, and it has been given that D takes 5 hours on machine M2, so the out time is 12 plus 5, that is 17. Similarly for E, in time will be 4, that is once D is out of M1, and E on M1 takes 4 hours, so out time is 8. Now E can be processed after D is finished on M2, so 17, and E takes 6 hours on machine M2, so 17 plus 6 is 23. For C, in time is 8, and out time is 8 plus 8, that is 16. For C, in time on machine M2 will be 23, and it takes 10 hours, so out time is 33. For G, in time is 16, and out time is 16 plus 7, that is 23. For G on M2, in time is 33, and out time is 33 plus 6, that is 39. For B, in time is 23, and out time is 23 plus 5, that is 28. Now for B, in time on machine M2 is 39, and out time will be 39 plus 4, which is 43. For A on machine M1, in time is 28, and out time is 28 plus 9, which is 37. For job A, in time on machine M2 is 43, and out time will be 43 plus 2, which is 45. Now based on this information, let us calculate the waiting time of jobs. So for F, there is no waiting time between machine M1 and M2 because F comes out on the first hour and goes into M2 at the same instant. So the waiting time is 0. For D, D comes out of machine M1 at the 4th hour and goes into M2 at the 12th hour. So there is a waiting time of 12 minus 4, that is 8 hours. For E, it is 17 minus 8, that is 9. For C, 23 minus 16, which is 7. For G, 33 minus 23, which is 10. For B, 39 minus 28, which is 11. And for A, 43 minus 37, which is 6. Now let us look at the idle time of the machines. So idle time of machines. Let's take machine M1 first. So on M1, it starts at the 0th instance, so there is no idle time in the beginning. Now it ends on the 37th hour, whereas M2 is still processing till the 45th hour. So on an overall basis, machine M1 is idle from the 37th hour till the 45th hour. So the idle time of machine M1 is equal to 45 minus 37, which is equal to 8 hours. Now for machine M2 is idle in the beginning when the job F is being processed on machine M1, and because we have the constraint that each of the jobs has to be first processed on M1 and then it will be processed on M2, so we have an idle time of 0 to 1 for machine M2. So the idle time of machine M2 is equal to 1 minus 0 equals to 1.